We are now moving on to our second module of Unit 8, introducing kind of the culminating topic of this course called hypothesis testing. Um, Confidence intervals are one kind of final version thing we learned. They put together most of the stuff in the big picture, and actually the big picture example was a confidence interval. But more commonly, a confidence interval is just a confidence interval is just an estimate. But more commonly, we want to actually make more of a decision. Has something changed? That was kind of the example I used at the end of the last video. So that is called a hypothesis test. And before we get into this, I want to give you a version that hopefully relates a little more. I'm just going to take some free space in the notes here. Thankfully, in the notes, there should be a page right before your page 206. And so this example here is uses the US court system. There's probably other court systems that are like it. Not all are exactly the same. And the court system for us, though, is very similar, almost identical, to the process of a hypothesis test. And so you have one good analogy. And I don't think this is anywhere else in the notes. So just kind of keep that in mind. It's not written, I think, in these notes, and I don't think I remember much of it on Canvas. So how does the US court system work? We're going for kind of like the idealized court system. I'm not a lawyer, a legal expert. If politics matters, I'm still not a political expert in all of this. I watch SVU and some Law and Order shows and stuff like that. So, but most of us are probably somewhat familiar, and that's kind of what I'm going to use as our example. So if my ideas aren't perfect, the logic process is very similar though. So the process of the logic in a hypothesis test involves, and maybe I'm going to take a little bit of a section to talk about that too, the idea of what's called like proof by contradiction. There's a few other ways to phrase that. Let's see if I can remember right now. I forgot the official, there's a technique in argument in what it's called. So one of the ideas is to assume what the other person, like let's say this argument between two people, assume what they're saying is true and to look for a contradiction to show that that must be false. So if we are arguing with someone who believes the earth is flat, right? The earth is clearly not flat, but you might not want to just say, you're ridiculous, that's wrong. So you might say something like, okay, let's try your idea that the earth is flat. And so you might believe that it's flat. And then, we're not going to go through the full idea here. Thankfully, I don't meet anybody who believes the earth is flat. But they might say, okay, if that was really true, then the sun should do this thing in the sky, right? Or other planets should be flat, whatever it might be. And then you say, but look, here is proof that we also can believe that that doesn't match. And so you arrive at this issue and some sort of contradiction, something's wrong. And what we can do is go back and say, that must mean the earth isn't flat. It doesn't directly prove that the earth is round. It's just saying not flat. And so that idea is built into the court system also, used in a slightly different way. And so I'm going to highlight the court system, just remind you of that logic, and that is how the method of hypothesis testing works. I think at the end of this module, we'll be able to give you some very simple techniques. So this is more for you to really internalize it really well. Okay, so I'm going to use the same 4-step ideas that our notes have. So our first step I've broken down the court system into 4 steps. In real life, there might be more than 4 steps, and I'm not covering every single aspect, more the logic process along the way. So in the beginning, there's everything about determining the charge. What the person is claimed to have done. Obviously, one side will be claiming they did something, one side will be claiming they didn't. Again, and everything we do later is going to mimic this idea. So there's going to be these 2 sides, 2 competing ideas. And a court case, this is an idealized court system, no abuse of the system whatsoever, so just keep that in mind here. A normal court case, you should only be there if there's already some evidence. There are processes that you can dismiss the whole thing if there's not at least some evidence. So that's the scenario we're under. Okay, so the person is a little sketchy. They were nearby when a crime happened. I don't know. They were on video, but it's not. You can't see them. Their car was there. Something like that. There's at least some minimum amount of evidence. They should be here under a normal court system, a normal court case. Okay, and so there is a very common thing assumed right at the beginning of a trial. So there is one thing assumed. And this is something you might be familiar with. It's a quite cliche phrase. I don't actually know if they say it in courts. Probably. We're going to assume that the person is innocent until proven guilty. So you get to assume, you're supposed to believe that the person is innocent even though they have some evidence with them, and then the process of the court case should try and change your mind. Well, one group of people are going to try and change your mind one way, and one group hope that you continue to think they're innocent. All right, and so you set up all of the initial court stuff, and you get to step 2, actually arguing the case. So we're going to collect and present evidence. Tried to word these as similarly as I could to the ones in our book. This one's pretty straightforward. The lawyers argue their case. It's going to actually be pretty straightforward in ours also. All right. Next, we would take that evidence and we assess the evidence. If any of you are very familiar with law or looking to be a lawyer, I could always use some input on how to make this more official. So a jury takes that evidence, and what do? They kind of decide the likelihood that the person is innocent. Because you're supposed to believe that they're innocent until you see so much evidence that you don't think they're innocent anymore. And whether these work like they're supposed to is totally not the point of this type of discussion. We could do some studies and statistics on how well court cases work out. Okay, there's another phrase here, a little less common. I believe this is like the standard of evidence, I think is what they call it. I like law a little bit. So beyond a reasonable doubt. So there's so much evidence left there that there's very little doubt that they did it, beyond a reasonable doubt. And once you've seen, there's no way an innocent person, this innocent person, could have so much evidence. I have to change my mind. And so we have to change, well, if we think they're, that's one of the outcomes. All right, on step 4, we're pretty much done now. This is the last step, and we're pretty much done with the idea. We just make a decision. And that decision is either guilty or not guilty. And like I said, all of this matches up. We have this idea of a reasonable doubt. Beyond it, we were going to have 2 outcomes. We are going to assume the person is innocent. To collect and present and assess the evidence, some of it is just going to be some formulas and some math that's going to tell us the likelihood. We still have a likelihood. We actually have an actual probability. And so that is our goal here. We're going to learn one very important number, one very important setup. So keep this in mind. I will reference it as a good way in case you have a hard time believing what we're doing. You can reference the court case idea. Okay, so just to highlight the big, we're going to learn of a specific concept called the p-value. It's actually just, it's a number. P, it's some type of probability. That's what we're going for. Conclude that's the most important, the most specifically important idea in this whole course. What to do with p-values. And it's in the context of a hypothesis test, but in general, what do we do with them? All right, and so remember, there are two final outcomes. Reject the null hypothesis, fail to reject the null hypothesis. These are the guilty and not guilty court case versions. I'm going to bring up the court case one last time for another example also. Okay, so compared to confidence intervals that estimate a number, hypothesis tests give you a yes or no answer. I think these are similar. No, these are similar to before. I don't know if they're exactly the same wording from Module 19. What is the average amount of money that community college students receive in financial aid? That's asking for a number, not a decision. Is the proportion, probably going to be yes, is the proportion of California community college students that qualify for, now called the Promise Grant, I believe, greater than 40%? That is something we can test. Yes, it's 40, greater than 40, no, it's not. Do the majority of community college students qualify for federal student loans? Majority just means 50%, so is it more than 50%? Something we can test. Okay, what are those four steps? Is those same ones that I outlined before. Determine the, this time, hypotheses instead of the charge. Collect the data and report the sample results. This time we go and take a sample from a population. Remember, that is our whole goal in this class. Our studies support that. Our probability we learned is to support this is the big idea. Studying samples to make decisions about populations. Assess the data. So those are kind of similar. We do all of our data crunching and come to a conclusion. And so just like the court case, there are similar conclusions here. Okay, 2013, a while ago now, survey of college students conducted by City and 17 magazine. 20% of college students have a credit card when they start. Is that percentage higher for community college students this year? So most of the time now, we're also going to have this idea of testing against us. We have to test kind of against some other number. So we have this 20%, has it gone up? So we need to do another, we need to get an additional set of data. So there's going to be this comparison. Before, in these quick wordings up here, the comparisons was kind of built in. Majority means 50%, greater than 40%, and then we have to go get a sample to check that. We sample 40 community college freshmen. In our example here, 25% have a credit card. So this is all going to rely on that sampling from Module 17. But if it didn't click there, you thought it was a little awkward, or if it did, that's great. You'll see how we use it in action here. And so that's why I wanted you to really focus on Unit 8 instead of 7 in how we do this. Okay, so we actually did this before in Module 17, and that's what's on the left-hand side. We have an hypothesis, 20% have a credit card, our claim is that it's higher. So now we have a very official way to write this out. So you have to follow this exact format. Fortunately, we don't allow any changes. So null hypothesis, so it's H with a little subscript of an O or a 0. It doesn't matter which way you think it is. Technically, we put a colon. And then we have to have a mathematical hypothesis. So this whole thing was about 20%, that it used to be 20%, is it different now? And so P, our population proportion, specifically right now, of community college freshmen with a credit card, 20%. And so our P is going to be equal to 20%. Fortunately, there's a lot of P. Unfortunately, there's a lot of P's. We're going to have to get really used to those. So P is 20%. We think for some reason it's gone up, and our sample data originally supported that. So that's the comparison to the person is going to be kind of sketchy in the court case. If we go and test it and it's gone down, it's a terrible idea for us to think that it would have gone up. But if it's gone up, we don't know if it's gone up enough that we can prove it's gone up. That's the big question. Great, so all of this is required for you to write down. All right, so collect and report the sample results. Sometimes that's as simple as reading the question then. So that these are, they actually match up better in the court case system. These are kind of really general frameworks. Sometimes there's not much happening there. To test the hypothesis, we went out and found 25%. In real life, that's a lot of work. That actually took the bulk of our time probably. But in terms of reading the problem, that's just kind of labeling all the values. Right, that's p hat, it's a sample. So is 25% larger than 20%? You probably didn't say anything out loud, but in your head, did you say yes? If you did, you have to be very careful. The whole purpose of this course now is to say, well, we should say, I don't know. I have to determine if 25% is far enough away than 20% for this sample size and this context to know that answer. Because, I'll give you an example, is 21% larger than 20%? You know, does it make a meaningful difference? Meaningful for us is just going to mean probability, but does it feel a lot bigger? Is 20.5%? And you can kind of see where we're going with that. Okay, so this new number we're getting, you've already seen it before. I'm sorry that this one is filled in there. So there's a bunch of bars you can't see because we printed that wrong. But so this is the one you've been seeing before, where we take the probability of that sample or more. That is what we're going to call the p-value. So this is the single most important number in the whole class. I don't know how many stars maximum I've put on anything else before, but it's this one, knowing what to do with p-values. If I could give you a single test, a single question for the entire class, it would be something about p-values. Right, in Module 17, we already touched on the idea of like, how big should this proportion be before you decide that your sample feels far away from the mean. And we said that that probability is probably somewhere around 5%. So 27% was the probability here, and that is quite large. So I don't know if that feels large yet, but our cutoff from now on is going to be 25%. Right, and so we've already mentioned this in Module 17, but that indicates that the survey, that the sample is not that unusual. There's a bit of a double negative there, right? I mean, I think grammatically it's correct, but it's not unusual. I guess that means it's usual, but we're wording like that on purpose. So it is possible that 20% is still correct. So our two outcomes now, they're back up here. Reject the null hypothesis, or fail to reject the null hypothesis. Reject is the guilty, and that's what we want. You know, I don't want people to go to jail in a court case or something, but they're normally there because they probably have enough evidence that they did it, right? The only reason they in real life you get to the court case is there's a lot of evidence. So there's that feeling also in statistics. Most of the time though, someone is trying to prove something right about their personal research they're doing. And so you want to be able to reject. And we'll see in a later topic why that matters so much. So keep in mind, we're really here to reject the null hypothesis. And again, our hypotheses are our two original bets. So those are like the people, one person in the court, one side of the court case is going to say they're guilty, and the other side is going to say, no, I'm innocent. And those are the two ideas. So you have to have two competing ideas. They're called the null and alternative hypotheses. They should be mainly about something numerical. And so we're studying population proportions, P. So the hypotheses for this one, just to remind us, are it's 20%. like it used to be. The null hypothesis in general should be the idea that things are the same. And so that's when that's the court case similarity, sorry, the alternative hypothesis should be different than that, and it should be exactly different, so it should be in some way opposite. This scenario, we don't care about being less, so it's either 20 or more than 20. We have to make sure they don't overlap and that there's no missing, there's like nothing possible to miss. The whole problem here also, this is what I was going to say, and I stopped a second ago, that this is assumed to be true. We're going to assume the null hypothesis is true. And so that's where we set this coin probability simulation thing that you've seen a little bit to 20%. So we're going to say, okay, I'm going to assume it's 20% and then see what are the chances of getting a sample 25% or further away from the mean. And so that's the example where you assume that a person is innocent. So the null hypothesis is essentially they are innocent, that there's really nothing happening here. The alternative hypothesis is the idea that they are guilty. And so we are going to assume innocence. Through the math, we assume the null hypothesis. Okay, so statistically, here are our wordings. So this whole scenario was called fail to reject. That's the official wording. That's the one I care about the least. That's great to talk to other statisticians, not so great to talk to anyone else. So there are two different versions here. This is the version from kind of module 17, I would say. The sample evidence is not statistically significant. That might be new words. But the next sentence I think you might have heard a little bit before. The difference between 20 and 25% can just be explained by sampling variability, can be attributed to sampling variability, which just means it's not far enough away where I'm questioning, is that not actually from, is the 25% not actually from a population of 20%? Oh, right now they're close enough that it could be 20%. And so in a more practical terminology, so this next sentence is really the one that I like the best here. We do not have enough evidence to conclude that more than 20% of the population of community college freshmen owns a credit card. So that is the big wording here that I'd like you to know, but all these other ones are similar. And that top sentence is actually really nice now, because fail to reject, nobody really uses that. And it's also just not used day to day. Purely for statisticians, no one uses it. The top is kind of common though. The evidence is not statistically significant. So you will often hear in research people say my results weren't statistically significant. And essentially they mean I failed to reject the null hypothesis because my p-value was too large. Okay, so our notes go through just a change of examples. So what if that 25% was still the same thing, but what if it came from a sample of 300 students instead? And so this will just give us kind of the hypothetical opposite conclusion. So the same hypotheses, the same 25% sample, but what if I had gotten it from 300 people? You had a very short discussion post about like how many coins to flip, similar idea. So find the p-value. So the p-value this time is 0.02. It's that area from our sample value and larger. You would calculate it. How would you do it if you had to do it on your own? You'd calculate a z-score and use the normal curve to figure out the area. But from now on we can use StatCrunch. So StatCrunch will have all of these options and how to plug it in and get that for you. Right, so this scenario now, so our p-value cutoff, our probability that's going to say when is it too big, when is it too small, is going to be 5% unless we're told otherwise. And so 2%, 0.02, is for sure less than 5%. So this now is telling us that 25% is really unusual. And our better guess is that the population value is really not 20%. Right, the left-hand side talks about the one you've been reading in 17. If that worked, that's great. This will be easier. If not, don't worry about it. The right-hand side is our final version. So this one, with a p-value that is small of 2%, we are going to reject the null hypothesis. Again, day-to-day, other statisticians, other researchers, you can very simply say the sample evidence is statistically significant. People will know what that means. But that's still not great for non-statistics familiar people. Then the next sentence is correct, but not a good idea. No one really phrases it like that, but that's to relate it back to what you saw in Module 17. And so you have this version here that kind of clearly explains it. We have enough evidence because our p-value is so small, or because our sample was so far away in terms of the size of the standard error. So we have enough evidence to conclude that more than 20% of the population of community college freshmen owns a credit card. And that is a strong statement. We are concluding something. Compare that to the previous one. The previous one was kind of a generic, a non-decision statement. We don't know. So the only time you get to conclude something is when you can reject, which only comes when you have a small p-value. Okay, so again, what is that probability? Normally 5%, but it's called the significance level, and someone will tell you that, or in real, like kind of real life, in research, most disciplines have an agreed upon amount, or they just kind of have how many different levels of significance did you reach, and they'll just kind of tell you all of them. Okay, I'd like you to grab all the sticky notes, highlighters, whatever you use. If you have the printed notes, if you have bookmarks on your tablet devices, if that's what you're using, bookmark that. If you haven't, download the PDF and print out this specific page, not 209, 210. These wordings here, p-value is the most important topic of the course. Again, I forgot, I'm not really using the star system correctly here, but p-value is the most important topic of our course. It helps us answer hypothesis tests, which it's a method of inference, which is our most important topic. So this page here simplifies it the most, these two paragraphs. What are your two decisions? When do you do them? And what are all the conclusions that are possible? And these next set of examples are the ones that are most important to help you get through that. Hopefully you can tell from our course, it's not about knowing the formulas to calculate. You do need to write those down, but you can use StatCrunch. It's about, when I get that result, what do I do? And a computer can even tell you what to do with that, but most of the time the software doesn't have all that built in because there's so much context to understand. So that is really the job here. And when other people do research and they give a result, you can then interpret that really well. Okay, so we're going to practice setting up a hypothesis. These two ones are just kind of very similar generic versions to the two outcomes on the previous pages. The top is if your p-value is small, you reject the null hypothesis. The next one is your p-value is large, you fail to reject. But those are in parentheses because those are not really the ones we want to hear you explaining with. They are the technical answers. People don't really use those in real life day to day. Okay, so in 2001, 74% of Americans favored testing in public schools as a way to rate the school. Your local school board conducts a survey to determine if a smaller proportion of residents in the district now support the use of mandatory testing in rating schools, 68%. So 68% is definitely less than 74. We were thinking it's smaller, so things are making sense. Okay, so what are the correct hypotheses? So from the last example, one thing we noticed is that the hypotheses have to be talking about the same number. If I'm going to bet that it's 20 and you're like, no, it's less than 20, well, I think the previous one was being more than 20%. We have to be talking about the same number. Those two are bad options. So what about the middle two? We have 74% as the one in 2001. We have 68% from our recent sample. This is p hat. This is p. Our hypothesis, you can see it's already written, is about p. And so it's the 74% one here. And this does agree it has the less than. Our sample came in less, so we should be testing less. We're going to skip part B. All right, so you have to set these up on your own. That'll mean usually typing it into StatCrunch. It'll type out the hypotheses for you, and then you'll have to know what to do with them. All right, interesting example here. 46% of high school students aged 12 to 17 in the US have had sexual intercourse from a 2014 study of blah, blah, blah. All right, is this percentage higher in inner city schools? So for some reason you think inner city schools, this is going to be higher. Right, so a survey finds 52% of inner city high school students have had sexual intercourse. So your idea is correct. It is higher. Is this large enough that it is actually higher, or is it just in kind of the gray zone? All right, so our hypotheses are written down. The 46% is the p, because the 52% is the p hat. All right, so the p is the population value, p hat is the sample. So those are going to be one of the two symbols. StatCrunch makes this nice. They don't really use a lot of symbols. They ask you in words. Right, the p-value comes out at 2%. So this whole problem is set up. P-value comes out at 2%. And is that significant? So again, our common cutoff is 5%. So is it smaller than 5%? Or larger than 5%. It'll never be exactly 5%. If it is, just round it to less decimals, and then you'll figure out which one. But it won't usually even matter. Okay, so this time it's smaller than our cutoff. Smaller is rejecting. That's like in the court case where you kind of internalize, you don't calculate things. There's such a small chance that this person has all this evidence. I'm going to say they're guilty. So that's what the p-value is telling us. It's a very small chance that the person, kind of is innocent. We'll talk about exactly what a p-value means, but that's the idea. Because what I said is not quite correct. Okay, so this is very small. Smaller than 5%. And so there's all those wordings. Again, 210, this page, mainly the paragraph at the top. Please print it out. Copy paste it, write in your notes or something. This is the most important page of your notes. Out of every single page of your notes, this one, we are at the most important topic. This is the most important page of your notes. Okay, so what do you do with that? Okay, so what does this mean about the p-value? Well, we already talked about this one. It means reject. It's not fail to reject. Okay, so we happened to talk about that one first already. So does it mean the sample evidence is unusual or not unusual? The small probability is talking about it being unusual. And so we heard that phrasing earlier, statistically significant. So we are looking for the unusual things. That's what we are hoping to see. So is that different? It is statistically significant. The opposite would be that it could be explained by sampling variability. Every time you sample, it's a random, but this one is so far away, we don't think it's the randomness that caused this. And then does this provide enough evidence, or does this not suggest that high school students are engaging in sexual intercourse at higher rates? This provides enough evidence. In this case, the person is guilty. There's no guilty here. This is about the court cases. We don't have that phrasing, but we have this result as being statistically significant. Okay, I think there's at least one more. These are some of the best examples because we're not focusing on the calculation so much. It's how do we interpret the results. Okay, we're going back to the slightly different survey. Okay, so 2011 survey, in any 30-day period, almost 12% of students in the 9th grade admitted to using drugs at least once at school. So there are a bunch of bad kids in these examples. Um, to investigate the issue in your community, suppose that the board hires a firm to conduct a survey of a random sample of ninth graders to determine if drug usage is higher than 12%. 75 students respond to the survey, to the anonymous survey, and 11 admit to drug usage at school, which is about 15%. This is a sample, so this is p-hat for sure. So this must be the p that we're talking about. All right, we're referencing 12%. And you can see here, the alternative hypothesis will be in the problem somewhere. They'll be telling you, are you trying to look for that it's more or that it's less? They'll let you know that. So, null hypothesis 12%. Alternative, so that's our school district is the same as the statewide answer. There's kind of no change. That's a very common word for null hypotheses, that there's no change. What is the alternative? That it's more. Our sample came in more. We're worried it's more in our area. Okay, so this is the simulation that's done. We will be able to do this without using the simulation. So it's not what we're going to use permanently. We're going to use just the z-scores essentially, just the normal distribution. Okay, but so the p-value is here. This is how we determine the p-value. It's this shaded region here. The population is set at 12%, and it's the probability of seeing samples greater than 15. So that p-value is 0.1825. Great, is that a big p-value or a small p-value? Cutoff is 5%. This is 18%, so it's much bigger than that. Are we looking for big p-values, or are we looking for small p-values? We're looking for small p-values, so this is not really the outcome we were looking for. This is the not significant outcome. Our data is not significant. Our sample was not unusual. We're going to have all of the answers that mean we don't know. Fail to reject the null hypothesis. The difference between them statistically significant? Nope. Survey provides enough evidence to conclude that the drug rate use is more than 12%? Nope. Okay, so I think it's the last two. Does not suggest that drug rate usage is higher than 12%, and that difference can be explained with sampling variability. This phrasing is the one that's important. It's the one that most people can understand. We didn't prove that it's 12%. We were unable to prove that it is higher than 12%. So be careful about that. I'll start talking about a little bit. In the court case scenario, you do not prove the person is innocent. When they leave it, the media and all of us might kind of assume that they're innocent if they came that back. Plus, in real life, a jury's they're making their best decision. Could be wrong no matter what. But if someone is not guilty, they are not saying they are innocent. You just didn't provide enough evidence to show that they were guilty. And that's technically different. I think I'm going to skip that. They're very similar examples again. If you'd like to go over those, we can talk about them later. I think I'm going to move on to our next module. Keep this a little shorter. We can always talk about these more if you'd like to come see me. Okay, so in the court case scenario, I'm going to take this example and do the court case one. The court case has what the jury decides and what real life is. Let me switch that to match ours. So reality and the jury's decision. So a jury can decide to say guilty. In reality, they could be guilty. And so that's the correct decision. There's nothing wrong there. This topic is about errors. There's two types of errors we can make. We don't know which one we're making at any given time, and we might not be making an error. So there's not guilty. The jury, the jury can say not guilty. In reality, that's not how you phrase it. You say innocent. If the jury comes back not guilty, the correct answer would have been if they were innocent. So there are the other two outcomes here. And I want to ask yourself, what is worse, sending an innocent person to jail or prison, whichever one it is, or letting a guilty person free? And I don't mean specifically like your personal moral beliefs. I mean, what does the court system decide is a worse scenario? What is the court set up for us to do? Since we automatically assume that they are innocent and change our mind to them being guilty, we should only make that when it's beyond a reasonable doubt. And so if we change our mind, decide they're guilty, and we made the wrong choice, that's the worst one. It's probably built on the moral question, but there is you can tell by all the safeguards of the system what's meant to happen, what you're meant to minimize. Innocent people convicted or guilty people left free. So we're going to give the worst error what's called a type 1 error. 1 is bigger than 2. And so a jury saying someone's guilty but they are really innocent is a type 1 error. A jury saying they are not guilty when they really were, so this is a guilty person let free, is not considered kind of as big of an error. I think that's the correct answer legally. Again, I'm kind of making a little bit of a guess there. But I also believe in statistics, that's why we're given the numbers. That the 1 is worse, the 2 is a little different. In reality, it really depends on the scenario what a worse outcome is. But, okay. So, for the statistics, there's this unknown reality, and there's our actions. So if we reject the null hypothesis, and the null hypothesis is true, I swapped these a little bit, sorry. And if the null hypothesis is true, we made a type 1 error. If we reject the null hypothesis and the null hypothesis was false, meaning the alternative hypothesis is true, we made the correct decision. Sorry, it's a little bit backwards. If we fail to reject, this is correct when the null hypothesis is true. And it's called a type 2 error otherwise. So here are the summaries. If the null hypothesis is true, but we reject it, that's a type 1 error. If the null hypothesis was actually false, meaning the alternative hypothesis was the true one, but we failed to reject it, that's a type 2 error. So type 1 error is often considered a little worse. And the probability of a type 1 error is interesting. It's just your significance level. But we won't go too much further into probabilities of errors. There is some ways to calculate them or to study them. It's the focus of a further course in this if you'd like to learn a little more about stats. Just a reminder, who learns about those? Psychology majors for sure, in addition to statistics majors, or anybody who does research, who sets up experiments and needs to clearly think about how to study them. There's a very common set of type 1 and 2 errors that a lot of you will be familiar with. We see it in media all the time. So, pregnancy test. There's what the test says and what the true answer is at that point. So, home pregnancy test gives a result of positive as pregnant or negative as not pregnant. Apparently, in a lab setting, home tests, and this is a long time ago now, are 97% accurate, 75% when used at home. We're not going to do probability in this. We're just going to study the idea of an error. Okay, so false positive and false negative means that there was an error. And so we want to think about what that means here. This is, I think, a good example. So we're going to set everything up as the null hypothesis is the woman is not pregnant. That's probably the best null hypothesis here, because that's the kind of baseline assumption, right? And then anyone taking a test, you know, a little while before would have probably thought they're not pregnant, and now they think they are. And so to make the decision is to move into they are pregnant. These ones aren't about the math though, right? So there's no numbers in these hypotheses. So this one's a little different. It's more of an example. So a type 1 error would be null hypothesis is true. But we rejected it. All right, so just you can turn back a page. They're up here. So type 1 error, the null hypothesis is true, but we rejected it. You don't have to really memorize these. Write them down. If they do show up on the unit checkpoints or a mastery quiz, there's probably only one question about these types of much more care about that p-value idea. Null hypothesis means true means they are not pregnant, but to reject that would mean to say that they are. But test was positive. And so medically this would be determined a false positive. And mathematically there's I think a pretty clear answer. Type 1 errors are a larger mistake. But that really depends how you line that up in real life. So let's see what happens here. Type 2 error, null hypothesis is false, but we fail to reject it. So this means that they are pregnant, but the test was negative. And so this is a false negative. So every medical test will decide are false positives or false negatives better. There's probably a common answer of which one is better either way, but they want to make sure that you don't have like too many people thinking they have some condition and then having to go test all of that, but you want to correctly identify a lot of the people with whatever condition, whatever it is you might be testing. So there's always a balance here. It's unlikely that all of these are 100% accurate. And so, you're probably familiar with COVID testing still, and so COVID tests have the same issue. How do they skew false positive and false negative? I don't remember, I can't find it anymore, but I remember one of the at-home tests that we had actually had the words false positive and false negative. I think I remember it saying a positive test is very accurate, meaning you do have COVID, but a negative test could be wrong. So I think it said something like there aren't a lot of false positives, but there are more false negatives. So that was, I think I remember that on one of the ones. I forgot to take a picture and then to use it for our course here. So that would be how we describe these. You might want to think a little bit about, does it matter which one it is in this case? Is one worse than the other? I think medically, in this case, a false negative is worse, right? This is a health condition. We have to now go to the doctor and possibly change our diet and our lifestyle a little bit if you're pregnant. And if the test says negative, you don't do any of that. A false positive, whether you're excited about it or not, you probably then follow up medically and then find out you're not. So I think practically a false negative here is worse. I was saying type 1 errors are normally worse, but how we set this up, a type 2 error is worse. I think this makes most sense here. So that one being worse than the other is not always possible. It's not always consistent necessarily, but it gives us a good idea. Okay, and then lastly, I'm going to go through this kind of quick. I think the notes on Canvas for this next set are pretty good. But what does that p-value number really mean? And so p-value is it's still built on assuming that the null hypothesis is correct. So if the population, this is the kids doing drugs, the 15% one, so all of that same example, and the p-value was 18%. This was the p-value. You do have to put p-value because we have p already as its own symbol. Fortunately, lots of p's in this class. There's even a p that we didn't use to describe very official probabilities, but you might have seen it on StatCrunch on the normal distribution calculator. Capital P is a different way to describe probability. Okay, so this one has a weird set of questions also too, but if the population proportion is 12%, that was the hypotheses, the null hypotheses specifically. How much samples, will samples as large or larger than 15% occur very often? This was p hat, and as large or larger was the alternative hypothesis, where we said that it should be greater. Sorry, not greater or equal to, I was just trying to emphasize that. Greater than 12%. So the 15% is the p hat. The probability of being larger than that, assuming the null hypothesis, that's what the p-value is. So the p-value is built on the assumption that the null is true. If you want the court case example, we don't, there's no real probabilities, but it's built on you assuming the person is innocent and then asking yourself some questions about that. Okay, so here is in context to this problem, in random sample from a population of 9th graders with 12% drug use rate at the school. That's the assuming the null hypothesis there. We expect to see variability. With a random sample of 75 students, there's an 18% chance, that's the p-value, that a sample will have 15% or more. So the 15% is the alternative hypothesis, or more is the, or more is the alternative hypothesis. 15% is specifically p hat, the sample value. All right, and then just one last way to word that, since this one's very concise, there's an 18% chance that a random sample of 75 9th graders will have 15% or more. Remind us, so 18%, that's the p-value. 15% or more, it's a combination of p hat with the alternative hypothesis, so we know which way we're looking. Reported drug usage will have 15% or more reported using drugs when we sample from a population in which 12% are using drugs. So that we still have to have a built-in null hypothesis. Okay, so every time it at least had the null hypothesis, the sample, and the relevant alternative hypothesis, and the probability itself, the p-value. So those are some examples. You'll see that in the notes also. I will skip these ones here, but they are good examples overall. So that finishes Module 20. 21 introduces some pretty small stuff, some final tweaks to hypothesis testing to really finalize it, and I think just one or two more examples. So really 20 was the big introduction to hypothesis testing. Just a quick recap. What is the most important thing? The p-value. You have to set up the hypotheses correctly, but you're looking for the p-value. And out of all your notes, what's the one page or piece of information from your notes you need to use and reference that really highlights, in a weird way, is the culminating ideas of all our course? It's these two paragraphs here on page 210. So page 210, keep that out as reference. If you have the physical notes from the bookstore, bring that to the front, put that in the front. Otherwise, print this out or just write out exactly what's here if you're taking paper notes. All right, I'll see you in Module 21. In 21, we'll finish Unit 8, and really the core of our course. We'll learn more types of hypothesis testing, but once you're familiar with p-values, The rest of the hypothesis testing is pretty straightforward. All right, I'll see you around.